So today we're going to take our geometric sequences and apply them to the real world. And that is done through exponential growth and decay. So our section today is Unit 1E, Introduction to Exponential Growth and Decay. It's in Chapter 8, Section 8, and you're going to notice the word introduction. We have a whole unit, Unit 7, on exponential functions, and we will revisit this topic. But today we're just going to kind of put a cap on Unit 1 by just where do we use geometric sequences. So when we left off with an n minus 1 geometric sequence rule. And I told you we would figure out how to write a more simplified version and it would come through the applications. And that's what we're going to do today. So you're going to just notice some pictures here. The money growing, you're going to see the bounce. When you bounce a ball, it drops lower and lower. And these are some ideas of geometric growth or decay. So the first thing we want to do is get our objective, which is to apply geometric sequences to exponential growth and decay. So here's our first problem. A small town started with a population of 2,000 people. The population of the town increases as shown in the table. Now, the difference between a geometric sequence and this application of exponential, in this case, growth, and what I mean by growing is the population is going up, that would be growth, is that we're not starting with our first term being called n equals 1. When we apply, we're talking about time 0. The clock hasn't started yet. We're going to start right now in 2000. And then we're going to come back a year later. So n equals 1 would actually already be having added, in this case, 200 more people. You'll see that. But we would have already increased the population when n equals 1, whereas when we're looking at our geometric sequence, we start sort of at that number 1. So that's the difference. We're starting at an n of 0, basically. And that's our initial value. Now, this population increase is a geometric sequence. So even though we add 200 here, we don't add 200. It's not arithmetic. The way you can see it's geometric is if you pick up your calculator and take 2,200 and divide it by 2,000, hit equals, and then come and take the next term, 2,420, and divide it by 2,200, and you should see that common ratio. Now remember, that multiplication is how we're going to write that, and we would be multiplying by 1.1. So 2,000 times 1.1 would give you 2,200. Multiply by 1.1, and you have 2,420. Now remember I told you that this is a little bit different than before. With our geometric sequences. So we're going to take and we're going to define our variables because it's a real world application. Our x, our input variable, is going to be the number of years, and our output variable, which I chose to be p of x, is going to be the total population, the 2,000, the 2020. So remember that we write a sequence. There's our output variable equals the first term of the sequence. In this case, it's actually the initial value. It's when n equals 0, when the number of years equals 0, starting point. And that's why we take that 1.1, which is the common ratio, and we're raising it not to a minus 1, but to an x. So when we do a geometric growth or decay, we're not going to put that minus 1. So now if we want to predict what the population is after 8 years, we would take 2,000 times 1.1 raised to the 8th. And when you put this whole thing in the calculator, you could see the population would be 4,287 people. Notice I put my units. It's a real world problem, so you should be putting your units on your answer. Define your variables and make sure you don't just put time. You need to know it's the number of years. That's important later on, months, days, right? And then don't forget to put your unit on your output answer. So here is our exponential growth. We're only talking about things going up, things expanding, things getting bigger. And here is our general formula that you might want to put on your notes page. So y equals a times b to the x. Y is going to be the amount at the end of the growth. What after the time period, how many people, how much money, what happens at the end. The A is our starting amount. We used to talk about it being the first term in the sequence. Here in the real world, it's some amount. It could be amount of money, the amount of people. We're going to multiply it by what is called a growth factor. The base of that exponent, if it is greater than 1, if the common ratio is greater than 1, so the 1.1 we just saw, your population, your money, whatever it is going to grow. It's going to get bigger. So if the base on the exponential piece here is greater than 1, it is a growth factor. And then the little x, which is your exponent, is the number of increases, the number of years, the number of months, the number of something, that time going by. So here's an example of an exponential growth function. There's the starting amount. Maybe it was $1,000. This is my growth factor, and I know it's a growth factor because it's a number bigger than 1. And then we would raise it up to how many of those increases, how many years, how many months, whatever it is that we're looking for. I just want to mention here, what would happen if this number was 1? What if it was 1,000 times 1, exactly 1, to some number? So what if it was 1,000 times 2 to the first, or 1,000 times, 1,000 times 1 to the first, or 1,000 times 1 to the fifth? If the base was 1, it equaled 1, your population is never going to go anywhere. It's not going to grow, and it's certainly not going to drop, because if this space is 1, 1 to any exponent is always 1. So if the growth factor, the common ratio, is greater than 1, your money, your population is going to go up, whatever it is. If it equals 1, it's going to stay the same. So here's an example. In the year 2000, Centerville had 1,000 cell phone customers. Each year, the number of customers increased by 25%. I'm going to complete a table, and we're going to try to talk about writing a function here. So the 0, the 1, the 2, the 3, the 4, that's going to be your number of years since 2000. So 0 would be no years after 2000, which means it's where you started, 2000. 1 would be 1 year after 2000, it'd be 2001, and so forth. We are going to use customers, and I'm going to use a Y there for our number, our output. So we started in 2000 with 1,000 customers. Now, what is 25% of 1,000? If you take your calculator and change the 25% to a decimal, think about what that would be. Did you say 0.25? If you take 1,000 times 0.25, that will be the increase. That's going to be the amount that's going to be on top of what you already had. So it would be the 1,000 plus, in this case, 250, and your new number of cell phone customers would be 1,250. Now, if you take that 1,250 and multiply that by 0.25 in the calculator, that's going to be your increase from 1 to 2. Add it to the 1,250, and you'll get 1,563. Pause the video and see if you can come up with the next two numbers. So the 1,563 times 0.25, add it back into the 1,563. You now have a total of 1,953. And then here you should have had 2,441. Now, there's kind of an easier way to get there. So if R is the constant percent of increase as a decimal, so we would make this 0.25, your growth factor would be 1 plus the 0.25. So instead of multiplying by 0.25 and then adding the 1,000, if you just come up here and take the 1,000 and multiply it by 1.25, you'll get directly to the 1,250. So if we multiply by a growth factor, which will always be 100% of what you already had, which is represented by the number 1, the whole, and add it to your increase, which in this case would be 0.25, your growth factor would be 1.25. So here is your function. The number of customers, call it Y, will equal the start amount of customers, which was 1,000, times your growth factor, which will be 100% of the population plus your increase. That's 125, which is a 1.25, raised to the number of years since 2000. And that's how we can write a function. So here's an example that I'd like you to try. The population of a community has been increasing at 8% each year. If the original population was 5,000 people, what will the population be in 10 years? So here's your job. It's threefold. Define your variables. Then you're going to write a general equation, not paying any attention to this 10 years. So you want the number of years to be a variable. And then you're going to substitute in your 10 and solve to answer the question. Don't forget to put your units in your answer. Pause the video and take a couple minutes to complete this problem on your notes page, guys, number 4. Okay, now your variables might be different than mine, and as long as they go through the whole problem matching, that's good. So I said that P was going to be the population, that's the number of people, and X was going to be the number of years. So now I'm starting with 5,000. That's going to be the start amount. So population equals, there's the 5,000, times, now my growth factor is not 8. We're going to change that to a decimal, which would be 0.08, not 0.8. That would be 80%. You move it 2 places, 0.08, and add it to 1. You need 100% of what the population was, plus 8%. So 1 would represent the 100%, and then the 0.08 would represent the increase, and there's your growth factor. And notice it's greater than 1, so your population is going to grow, and then I'm raising it to the X. That is called a general equation. Next thing we're going to do is substitute the 10 in for the X, and you're going to show me that, and then pick up your calculator. Take 5,000 times 1.08, raise it to the 10th power, and the new population of this community would be 10,795-ish people. Now you had a decimal. We're going to, go to the whole person, not leave a decimal out there. And to be honest, whether you round up or round down with people, we can talk all day long as to whether we should cut that person off or count them as part of a person. So I will accept it either way. Okay, so that's exponential growth. Let's go in the other direction. What happens when things go down? Population goes down, you lose money, or in this case, you bounce a rubber ball. So let's say you drop a rubber ball from a height of 1 meter. That's our start height. So at 0 bounces, in my hand, it's 1.0 meters above the ground. Every time it bounces, it will be 80% of the previous height. So 80%, take the percent sign off, move the decimal 2 places to make the number smaller, would be 0.8. If you take 0.8 times 1, the second bounce will only go up 0.8 meters. Gravity's pulling on it. It's not going as high. And then if you take the 0.8 and again multiply it by 0.8, the second bounce will only go up 0.64 meters. Pause the video and finish these two to find out how high will the fourth bounce be. So if we come to the third bounce, it would have been 0.512 multiplied by 0.8, and that fourth bounce will be 0.4096 of a meter, less than half a meter. Now I want to talk about decay factor. So this was the original height. So right here is 100% of where we started. When it bounces, it only comes up 80%. So where I'm drawing a line, that's 80%. It lost 20%. So it dropped 20% and 80% remained. your decay factor is always the amount that remains. So in this case, your decay factor would be 0.8. Kind of gave it to you in the problem. So to write a function, we would again, we're going to define our variables. So I'm going to let f of x be the height of the bounce. And again, now I have to use x for my input. That's going to be the number of bounces. So f of x equals my start height times, and I need a decay factor this time. It's going down. So it would be that 0.8 we just talked about, how much remains, raised to the x. And then I could find out how high it is off the ground for however many bounces. Of course, in this case, at some point, it will come to a rest due to gravity. We could have asked this same exact question a different way. Same question, but a rubber ball is dropped from a height of 1 meter, and the height of each bounce is 20% lower than the last bounce. That is the exact same question. This time, they're giving you what was lost rather than what was left. So your decay factor is still 0.8. It's still bouncing 80% of where it was. And that would give you that same function rule. So here is the model for the decay factor. Let me just move him. I don't know why that. There we go. A situation where a quantity is going down with a common ratio is known as exponential decay. And the way you can remember is the word decay. Think of down, decay, death, depreciation. I say all the D words tend to go with exponential decay, and it means it's going down. This looks like the identical slide I showed you a minute ago. We still have y equals a times b to the x, but this time your common ratio is between 0 and 1. It's less than 1, and we really don't talk about a negative b when we're talking about a real world situation. So it's 0.5, it's 0.7, it's less than 1, but not negative, basically. And so here's an example of an exponential decay. The minute I see that this base on the exponent is less than 1, my population, my money, whatever it is going down. It's a decay. It's a drop. So I just want to remind you that, when a situation has a constant percent of decrease, the decay factor is going to be the population minus the rate. So if they give you the rate of drop, how much it decreased, so it went down 30%, it went down 5%, then the way you find that decay factor is to take the 100% of the population minus the percent, or in decimal form, 1 minus whatever the decimal is. So let me do this one with you. 5% would be a decimal of 0.05, not 0.5, guys. That would be 50%. So around the 5 and add a 0, 0.05. That is not your decay factor. That's how much came off. You need to know what is remaining. So if 5% came off, 95% remains, so your decay factor would be 0.95. Kind of drew the picture for this one over here. This is saying that 30% dropped off. So what percent is remaining? 70%, which would give you a decay factor of 0.7. Can you fill in these last two with the decimals? Change this to a decimal, 0.106, and take 1 minus that. Did you get a decay factor of 0.894? And the final one, number 4, 4.5%. Now there's two directions you can go. You can take 100% minus the 4.5% and then change it to a decimal. Or you can change the decimal the percent 4.5 to a decimal and then subtract it from 1, which would represent the 100%. Either way, did you get 0.955? So in 2002, each person in the U.S. drank an average of 207 pounds of fluid milk per year. Since 2002, this average has decreased by 2% each year. Write a function to model the change in milk consumption. So the first thing you're going to do in a real world is we are going to define our variables. And what are the two things that are changing here? The year is changing, and that amount of milk being drunk is changing. Consumed, I should say. So actually, let me put this over here so we can see this. So the first thing we want to do is define our variables. So T is going to be not just years, but the number of years since 2002. And I'm going to let M be the milk consumed per year in pounds. So what I'd like you to do right now is just pause for a second, or I'll give you a second, and just think, what will the decay factor be here? 2% decrease, not 2% left, but 2% left, then your decay factor would be 98% or 0.98. Now we're going to write an equation. M, the amount of milk per year in fluid pounds, equals my start amount, there it is, times my decay factor raised to the, in this case I use T, the amount of years since 2002. There is my general function. We can put him back over here too. That's the second step. Finally, use that function to predict the milk consumption in 2014. Now, we're not just going to slap a 2014 in T. That's where you need to see it. We need the number of years since 2002. So from 2002 to 2014, how many years have gone by? So our T is going to be 12. So now I go back to this, and I substitute 12 in for T, and I pick up my calculator. 207 times 0.98 raised to the 12th, and there will be about 162, and don't forget your units, they're right here, pounds left after 2000 or at 2014. So just to kind of leave off with a note here, exponential growth and decay functions is the general formula is y equals a times b to the x, where a is your initial starting amount, and b is either going to be a growth factor if it's greater than 1, or a decay factor if it's less than 1, raised to the number of some kind of increases, months, years, or times. So that is the application of geometric sequences. We do an entire unit on exponentials coming up in Unit 7. It's way on the other side of spring. So we will revisit this, but here, if you were to ask me, where do we use this stuff, Mrs. Woodruff, I'm answering it for exponential growth and decay for geometric sequences. Have a great day, everybody.